Dear students, today we'll be looking at an additional topic which is sensitivity of PMMC instrument and the loading effect. So sensitivity, we have already seen this particular term. It is defined as a change in output to change in input. So we have already seen this. Now in case of a PMMC instrument, the deflection torque is given by this particular equation BINA, and the control torque is given by Kc into theta. At equilibrium Td is equal to theta. So when we equate these two, we can write theta by I will be equal to BIN divided by Kc. Now theta by I can be defined as a sensitivity, that is output is your deflection and input is the current that is being flowing in the moving coil. And so this is BNA. Okay. Now assuming that your flux density and area of cross section is remaining same, you can increase your sensitivity by increasing the number of turns. Okay, once you're increasing the number of turns without changing the area, what you can say, you'll have an increase in the resistance. So resistance of your particular meter increases as the length increases. Okay, and also you can increase sensitivity by reducing the value of this spring constant Kc. So these are the two methods by which you can change your sensitivity. Now on a meter dial, the sensitivity is also defined in terms of resistance of the meter for 1 volt range. That is in ohms per volt. Okay, sensitivity is also defined in terms of ohms per volt, and it is defined as 1 by IFS, that is full scale current reading, or it is VFS for voltage scale. So in whatever way, this is defined as I by full scale reading, that is a current that is required to produce full scale deflection, that is given by IFS, or this also can be termed as IM in our previous examples. IM, it is a current that is flowing through the instrument, IM. Okay, so keeping this particular thing in mind, we'll look at the next case. So remember, sensitivity is defined in terms of ohms per volt. If you take the inverse of sensitivity, you will get the current I full scale reading, or the current that is flowing through the instrument, IM. Now loading effect is the degree to which a measuring impacts the electrical properties of an instrument. The properties can be voltage, current, resistance, etc. of the circuit. Okay, so you'll have certain elements in the circuit, and once we start measuring, some of these properties might vary due to the instrument. Some properties might vary. So we'll take an example and see how this sensitivity and loading effects can be explained. So in this example, it is decided to measure the voltage across 50 kilo ohm using two voltmeters A and B. A has a sensitivity of 1000 ohms per volt. So this is how you specify your uh, uh, sensitivity, and B has 20,000 ohms per volt. So now range of the voltmeters are 0 to 50 volt. Now from this data, sensitivity of A is 1000 ohms per volt. What will be IM? IM will be 1 by 1000. Okay, so that is 1 milliamperes. So already this is ohms per volt. So when you take the inverse, you will be getting it in amperes, or it is in milliamperes. Okay, so that's how this way you can find out the current that is flowing through the instrument. Okay, now if you don't have a voltmeter, how will you measure the current? You can do the voltage division. So once you divide the voltage 150 among this 150 kilo ohms, you will be getting 100 volt across 100 kilo ohm and 50 volt across 50 kilo ohm. So that is a very true concept. Okay, so your true value will be 50 volt. Now before the connection of the voltmeter, voltage drop across this 50 kilo ohm is 50 volt. So that is what you mean by this particular true value. You are getting 50 volt across this particular 50 kilo ohm. Now you are verifying it and this true value with the help of two voltmeters, that is A and B, with different sensitivities. Now case 1 where voltmeter A is used. Now sensitivity of voltmeter is 1000 ohms per volt. Now the resistance of the voltmeter, internal resistance of the voltmeter can be found out by using this sensitivity into voltage. So you are using a 50 volt range. So you put your choose your voltmeter into a 50 volt range, and then the internal resistance will be 50 kilo ohm. It is the total internal resistance, that is meter resistance plus the series resistance. This together comes out to be 50 kilo ohm. Now once you have a 50 kilo ohm connected like this, 50 kilo ohm connected like this, what happens? The equivalent value of voltage, what will be the equivalent value? It will be 25 kilo ohm because you have 50 and 50 in parallel. Okay, 50 and 50 coming in parallel, and now the voltage across R equivalent, this will be 25 into the total voltage 150 being applied across it divided by 100 plus 25, which is 30 volt. Though your true value was 50, once we connected a voltmeter of sensitivity 1000 ohms per volt, we are able to indicate only 30 volt because this voltmeter also in turn acts as a load for this particular 150 volt. So 150 volt is this 150 volt source is seeing this 50 kilo ohm voltmeter also as a load. So it is acting as if a load is connected here with value 50 kilo ohm, which is equivalent to the load which is already present. So in such a case, you are getting only 30 volt across it because rest of the 120 volt will be coming across this 100 kilo ohm. Okay, I have only 30 volt coming across it. So your voltmeter here reads very less when compared to the true value, and for getting good accuracy, the resistance of the voltmeter has to be much greater than the circuit resistance. So that is the thing that you need to keep in mind. Now we will change the voltmeter. Okay, so here voltmeter B is used, which is having a higher sensitivity, 20,000 ohms per volt. Now the resistance of this particular voltmeter will be 1000 kilo ohm. When you multiply sensitivity into voltage, you will get the internal resistance. So you are connecting, suppose you are connecting 1000 kilo ohms here. Now the equivalent value of resistance will be between these two will be 47.6 kilo ohm, and the voltage across this particular setup that should be measured by this voltmeter will be 48.3. Okay, now you can see that the sensitivity of B is much higher than sensitivity of A, and because of that, error in reading has reduced. Now the resistance of voltmeter is much higher than circuit resistance also. Circuit resistance is 50 kilo ohm, which is to be measured, and here you have 20 times the circuit resistance being applied here. So the voltage reading is close to true value. Okay, now the particular effect of loading is seen here. So here your instrument acts as a load and you are getting a very low value as the measured value. But here, once the sensitivity increases, your measured value is now closer to the true value. So what you need to understand is that loading effects can be minimized by using voltmeters of higher sensitivity or higher ohms per volt. So in such a way, we can reduce the loading effects. So loading effects is simply uh, that you are connecting a voltmeter, and this voltmeter is in turn affecting the properties of this particular circuit, that is by altering the resistance of this particular circuit in this particular example. Okay, so hope you have understood how to use sensitivity in practical problems. You can get the internal voltage from sensitivity equation. Also you can get the current through the this particular internal uh, meter, internal resistance of the meter, IM, meter current from the sensitivity. So keep that in mind. So